of large volume string models.
Okay, well, thank you very much for the invitation. It's nice to be here. My talk is supposed to be about the astrophysical mathematical implications of our model that I've been working for a while, large volume models. Although the organizers were complaining that there are not many talks in phenomenology. So I decided to squeeze a couple of experiments on phenomenology. So the exchange to get 10 more minutes for my talk, I guess. Okay. So I will be quick on this model stabilization that Andre already mentioned, and I think Renata and other people will mention later on. We will be working in this context of this KKT scenario, in the sense that we start with a type 2B string theory and a Calavillado, turn on some fluxes of three forms, and they generate a superpotential that gives rise to a scalar potential that fixes a large quantity of large class of moduli, like a complex structure model and a megaton, and then we are left to fix the scalar structure model. That means that the size and the shape of the extra dimensions, and that is usually done by adding number 2 at the effects to the superpotential, using the standard expression for the scalar potential known for Calavillados, give you you plug that into the scalar potential and that fixes all the scalar structure moduli, which comes all of them in this exponential, or the ones that comes in the exponential are fixed. I have to emphasize that this scenario of the KKLT, they assume W0 to be very, very small, such that you can compete with this exponentially suppressed quantity. So W0 is very, very small. And that's what the change that, one of the important changes that we will make in our proposal. This is the picture of the Calavillado. These are membranes that give rise to the number 2 superpotential. The fluxes just like the growth, and you can put under these 3 brains there, or something else to lift the vacuum to the superspace. So that was a short review. Any questions? Okay. So let me just start with the exponential large volume, which are the things that we have been working for a couple of years already. Okay, so the starting point is that what we wanted to do is to generalize as much as possible the KKT scenario. Before I did with the Palascomayan, Berkeley, and Connor, and Sulis. And the starting point is that we start with the Calavillado manifold, which is the extra dimensions, for which the number of complex structure moduli is bigger than the number of scalar moduli, and both greater than 1. This because of mirror symmetry in principle, there is this is essentially half of the Calavillado manifolds. And include to the scalar potential on the supergravity effective theory, the scalar potential has a alpha prime correction, so leading order in the alpha prime correction, so that without that it was just the log of the volume, and now we have this extra factor. And as a particular case, as an example of this model, we have a model with 2 scalar moduli. This is a particular Calavillado called P1169. So it has 2 moduli, for some reason called tau 5 and tau 4. And so knowing that the volume takes this form, notice about this minus sign, which is important because it's very typical in the Calavillado manifold that the volume has this minus sign there. And you plug this volume into the expression of the scalar potential, and then just can compute the whole scalar potential, knowing that the superpotential is exponentials for the corresponding fields of 4 and 5 that you can find. And once you do this, what you find, just plug that into the scalar potential, what you find is that the volume is the exponential of AS tau S. S tau S I call the small one, tau 4. And the volume, I'm exchanging it for tau 5, because out of the volume of tau 4, I can only find tau 5. And the important thing here is that the volume comes out to be the exponential of tau S. So tau 5 is exponentially larger than tau 4. Where tau 4 is this constant size, essentially, that I have here, divided by GS, where GS is spin complex. So tau, the small volume, the small cycle that I call small, this is of order 10 or so. This is suppressed by 1 over GS. So if you start the string is going to be 0.1, you get something of order 10 or 20 given this number. And then the volume is the exponential of that. So it's a huge volume that I can get. So that is particular about this class of models. I emphasize that I'm using this as an example, but there are many examples satisfying this property for which we get the same result. So this is the very general property of these models, and that's what we call the exponential large volume models. Okay, so I don't think I said it, but this moduli tau 5 and tau 4 are sizes of 4 cycles. And so that means that we have a huge 4 cycle, and the other ones not that large. To be more explicit, the scalar potential is written in this way. This part is the complex structure moduli and the dilaton part, which is suppressed by 1 over the volume squared. And then it will be minimized when this covariant deviates, so W will be 0, so that will fix its fields as before by fluxes. And then we are left with these 3 terms. And then these 3 terms, you can see why you get exponential large volume, because you take the volume to be e to the as tau s. These 3 terms are of the same order. And then you can get a minimum, and you can compute with each other to give a minimum. Interesting from this is that you get a minimum for any value of W0, or say between 1 and 10, or any value. We don't have to continue to be very small. And that's where we differ with the KKLT scenario. For instance, that we can consider W0 to be relatively large, which is more generic. The interesting thing from here is that once you find the minimum, this is what let's say the minimum will be around here. The string scale is given by the standard formula. A string scale squared is inclined squared divided by the volume. And since the volume is very large, then we can get all the scales that we want. The Goff scale, the Green scale, or the PV scale, they come out very easily by just, for instance, just take the string scale to be 0.1, divide n, where n is the number of these 7 branes trapped in 4 cycles. Take n to be 3, you get a TV scale. Take n to be 22, you get a Goff scale, for instance. Dividing a small range in an integer number, you cover the whole range of scales from the TV to the Goff scale. So that means that the string scale can be as small as you want. And to compare with the KKLT scenario, what we can just start varying W0 and making it smaller and smaller and smaller. And at some point, our minimum, you will see our minimum, and then you will see the KKLT minimum appearing also there when W0 is very small. And at some point, they seem to merge, even though they still keep a separate minimum, because ours is non-supersymmetric and theirs is supersymmetric. But that's to give you an idea of how the KKLT minimum appears on this. So how can we use this for phenomenology and for cosmology? Is what I will move on next. And this is what we call a modular model building, in the sense that I'm talking first about the Calabi-Yau that is being fixed by the modular. So the picture we get is that we have a huge 4 cycle that will determine the volume, and then we have a bunch of smaller 4 cycles, where in one of them we can have several D-branes wrapped in there, and then you will get the standard model. And by this, so that means that the physical standard model will be localized, and then the physics of the moduli stabilization and so on will depend on the whole bulk of the manifold. And this is a realization of something we called a few years ago the bottom-up approach to string constructions, in the sense that you can separate the local issues from the global issues. The local issues is how to get a gauge group, say equals to 1, the Carroll spectrum, the Kawa couplings, here with 3 families of course and left and so on, the gauge unification, proton stability, etc. So these are questions which are local, of where we do the standard model. But then we can separate slightly from the global questions of model stabilization, the breaking of supersymmetry, which will usually be broken by a modulus field filling the whole bulk of the Calabi-Yau. Then from that you can compute the soft terms, where the standard model fits. Issues about the cosmology, the constant and inflation and so on are global. So we can concentrate on these questions, and then after controlling that, we can just pick our favorite model of branes give you something realistic and plug it into the corresponding force cycle. That's a way of separating the two questions, and that makes the model building much more under control. I have to emphasize that the separation is just up to some stage. At some point, you have to connect it to things. If you have inflation, you need reheating, so then you need that part and so on. And we have been trying to include as much as possible from the other side. But in my talk, I will just concentrate on this global issue rather than the local. I will not give you a concrete model with the families and so on, but I will talk about the model stabilization and what is the physics that you can extract from that. The interesting thing is that in these models, you can put the standard model in either on D3 branes or D7 branes. Those are the two options. If you put it on D3 branes, we don't get something very exciting. Well, we get a version of what Savas calls Spitzus, because we get the supersymmetry breaking scale to be very large, and then we have to tune to explain why the Higgs is small. The Higgs mass is small. So, but that doesn't solve the hierarchy problem in the standard way. Whereas if we put the standard model on D7 branes and get the volume such that the string scale is 10 to 11 GeV, then with W0 of order 1 without, that means no fine tuning, essentially we get the gravitino mass to be the TeV scale. And once we get the gravitino mass of TeV scale, we can just compute by knowing how the chiral matter feels. The standard model using on D7 branes, you can compute the Keller potential for them. That's something that we did recently. And then read from that the self-correcting terms. So let me just tell you how this works. So you have the Keller potential for the moduli fields. This is the part I've been talking to you about. Is the Keller potential. The Keller moduli part is the complex structure moduli and dilaton. The superpotential is the flux part, and then the non-perturbative part. But then when you couple that to matter fields, living on D7 branes, on the standard model side, you have the superpotential will be the one that we had plus the coupling to matter fields. The field C is the typical matter field, the quarks and leptons, for instance. The Higgs are separated because they are special, so it's even by themselves, the unit term. The Keller potential, you can write an expansion in powers for the matter field, so you have quadratic piece on them and then plus other terms. And then this is the basic derivative function, so it depends on the model. And as I told you, these coefficients here, they needed to be computed for chiral matter on D7 branes. And once we know them, like this point, the function of the corresponding modulus and the volume, we only know the Keller modular dependence, the transfer function that depends on the complex structure that we don't know, but that is not relevant for the software terms. So once we know that, and see how supersymmetry is broken, because the minimum is anti-de Sitter, so non-supersymmetric as well. So then we can compute the supersymmetry breaking terms. And the soft terms become all proportional to the gravitino mass divided by this ratio, the log of m prime over m3 halves. So that means that the gravitino mass doesn't have to be a TeV, it can be a order 20 TeV or so, such that the soft term, the splitting of the multiples of the symmetric part of the standard model can have a value of 1 TeV. For the simplest case that we have is that where the branes where the standard model wrap the same cycle, we have an extremely simple expression for the soft terms. You remember at some point, Sue said that to solve the hierarchy problem, what we had to do was to introduce 105 parameters by hand in the supersymmetry. Here, we solve the hierarchy problem because we have the right scale, and there's only one parameter, which is essentially the masses of the genome. So the genome mass is scalar mass, the trilinear couplings, trilinear inter which are subterms, and this is the inter, which is the Higgs mass. These are all the four soft-supersymmetry breaking terms, and they are all depending on this capital N mass. So essentially, we reduce all these 104 parameters to essentially the genome mass. Or essentially, this, and they're all the same because they're all proportional. This is the F term of the small cycle divided by the size of the small cycle. This is one parameter, and from that we determine uniquely all the other soft breaking terms. So that means that this 105 parameters that Suber is mentioned is only one parameter. And it's something that we don't put by hand, I insist it's something we derive. and we get this right scales. It's important because that gives us universality. That's an important problem about supersymmetry breaking, is that precisely all this, if you have many other parameters, the coupling will not be universal, and there are strong constraints to experiments. They don't give you also no extra CT violation phases, so again, they don't have to do the experiment. There is one scale, which is the string scale 10 to 11 GeV, and all the subterms are suppressed by the Garavito magnetic block. So that is encouraging for phenomenology. And we can explain actually the source of universality by the coupling of the two kind of fields. The fields that couple to the standard model, I call them flavor. These are the complex structure model, whereas the fields that break supersymmetry are the Kenner model. And so the ones that break supersymmetry don't give you the flavor, so they're universal. And the ones that give you flavor they don't break supersymmetry. So that explains why the supersymmetry breaking terms are universal. From here on, you can try to go all the way to the LHC, but now we have found the supersymmetry breaking terms, the proper hierarchy at the string scale, and from then on, all the techniques are well known. You can start from the subterms at the scale of the string scale, then do the normalization group running all the way to the TeV scale. There's some codes that are very available to do that. Then, after doing that, you get the spectrum and all the physics at low energies at the TeV scale that you can compare with LHC. And moreover, you can have event generators like Kitty and Harry, just plug your data into video. And on top of that, you have detector simulators. We use something called DGS. And actually simulated clean inverse femtobands of data for LHC. And after that, you can do data analysis, reconstruction, and so on, which are standard things. This is actually, we can do that. It's a lot of computer work, but we happen to have a grid in Cambridge, 150 computers working simultaneously, and we were able to come out with a unique thing, which is like the first 2 years of running of LHC. And just to give you a flavor of what we get, for instance, a spectrum of all the supersymmetric particles with different masses and so on. And here's more tutorial. I won't go into the details of this because my talk was supposed to be cosmology, but just to give you a hint, we can also compute all the allowed parameters by constraints like B to the gamma and the right dark matter abundance and so on. So we get a regional parameter space that is allowed, and so on. So there's a lot of nice phenomenology coming from this, and that is the motivation for this model. So why is it that the string scale is of 10 to 11 GeV? Because we have the volume to be exponentially large, and if we get the value of 10 to 11 GeV, we get the right gravitational mass and then all the nice physics to use supersymmetry to solve the hierarchy problem. So now we have that, we can ask what are the implications of these models to cosmology. And the implications are several. First of all, you can play this with this potential to get inflation, something we did a year and a half ago or so. And the nice thing, you get this potential, you can see the exponential part plus a constant part. This negative exponential gives you very flat potential coming down. And this second exponential, when the tau becomes smaller, it gets important and gives you a minimum. And that's perfect to get inflation, which is very slow roll. You can get small field inflation, no fine tuning, and the spectral index in the right range. This is something we did with Condon, and then Von Goffman and Pushkin added the extra direction of an axionic direction and found even more trajectories that give inflation. So this is very nice. This is, I think, the only case I know from string theory that you don't have to fine tune to get the slow roll. And however, it has some problems, and the two problems I will mention, I think Andre mentioned a little bit, and Renata will talk more about this, is that this works to get the right density perturbations. We have to get the scale to be essentially close to the God scale. Whereas, as I told you, for all the phenomenology, the string scale had to be 10 to 11 GeV in this scale. And so this is a particular realization of the problem that Renata and Andre pointed out a couple of years ago, that you want to get the right scale for density to perturbation from inflation, then the gravitational mass comes out too large. And this is how it will be. If we have the string scale to be God scale, then the gravitational mass is much bigger. So that's why we were imposing into 11 GeV. So this is an open question. We have several ideas about this, but no real answer at the moment. Guy was giving me some ideas about using his way of generating perturbations to specify high inflation of low energy, but some we have to work out. But this is something interesting to think about. The other question that we have open is loops. This potential I told you is using leading ordering alpha prime expansion. Then you have those are dominant over stream loop corrections. It has been shown recently by Hack and Tat. But so once you have something which is very flat, you have to worry about the next leading contribution that will ruin that flatness and it ruins it to which extent. So that's something. Initial conditions, yes. Well, we argue here that we don't know the initial conditions, but we know the final conditions. Final conditions, all of them have to be stabilized, and this is different from, say, from brain inflation. And here you say, well, whatever you start, this is the last modulus to get stabilized. Okay, so let's move, leave inflation for a while, for a moment, and then see what is the cosmology of these moduli fields that we have, because these fields are there. This is a generic prediction from this construction. Essentially, for all the string compactifications, we always have this moduli. And in our case, at least, we have a well-defined way of fixing the moduli, and we know exactly the properties. We know the mass and so on. So we have to explore what kind of physical implications we can get. So, for the dilaton and complex structure moduli, the masses are suppressed by 1 over the volume, so they're close to the gravitino masses. The heavy the moduli which are corresponding to Keller modulus, which are small means of order 10, which is large for everybody else, they are suppressed by 1 over the volume times the log of m Planck over m T-has, which is a 440. So these are much bigger than the gravitino mass. So this is interesting already. So the gravitino mass was like 30 TeV because they have to be bigger than the soft terms. This is another factor of 30 over the gravitino mass, so this is order 500 TeV or so. So these fields are heavy, and so they are not generically of the order of gravitino mass as people might assume in the past. But the other case is the other way around. The field corresponding to the large volume, that is a very light particle because the mass was proportional to 1 over the volume to the 3 halves. This only was 1 over the volume. It was 1 times log. This is 1 over the volume to the 3 halves, and the volume is so large, this mass is essentially, well, the Planck scale times m 3 halves or m Planck to the 3 halves. So in the 10 to 11 GeV scenario, this comes to be of order 1 MeV. Okay, so we have 500 TeV and 1 MeV. These are the size of the masses of these particles. So we have to explore what to do with them. And so in the particular case of two moduli that I've been discussing, there's some, you have to do some massage here to go to the canonical normalized fields that I call capital phi and pi. This will be the heavy and this will be the light. And so both of these fields, the big and the small, have contributions from the heavy and the light, but different contributions depending on the volume and different powers. So this field, the big one, is mostly pi, which is the light one, because it's only the 2/3, whereas the other one is mostly capital phi, because the volume to the 1/2 is order 1. But since they are mixed, so we can see that even though we have the standard model living on the small brain, on the small cycle, they still couple to the large cycle because there is this mixing. And so from them, we can compute what the decay rates of each of the particles. So you have the lambda, chi, gamma, gamma decay rates. These particles, the chi field, which is MeV, can only decay into photons and electrons and positrons. Electrons and positrons. And of course, neutrinos, but they are suppressed. Whereas the field capital phi can decay more things because it's heavier. And this is a summary of the numbers we get. So for the light modulus, if you have a lifetime of order 10 to the 25 seconds by knowing that the inverse of the decay rate for electrons and positrons or gamma gamma. But notice this is very important. The branching ratio to go to photons is very small. So the dominant decay is to E plus minus. So this particle decay mostly to E plus minus, or 0.97 and this is because of the coupling the coupling to the gamma is suppressed by this famous law, whereas the coupling to the E plus minus is not suppressed by that, so it's a factor of 30 in the coupling and a factor of 30 squared in the decay rate, so that will give you a dominant contribution to the branching ratio to the E plus minus and to gamma gamma. The heavy moduli, on the other hand, since they are heavy, they also couple, when you compute the coupling also presses not by 1 over n line, but by 1 over n string. N string is only 10 to the 11 GeV, so the couplings are very strong compared to. So this is again against standard intuition. So these fields couple very strongly to matter, and that means that they also can decay very fast. And the decay time is 10 to the minus 17 seconds compared to the other one is 10 to the 25 seconds. This is still alive. So the physics is very interesting, and so we have been exploring in the recent paper with Joe Conman the implications of this for cosmology. The typical problem to address is called the cosmological moduli problem, something that people had investigated in the past and called it Polonic problem, but 30 years ago we came with the Carlos Casas and Roulet and also Banks and Medicine. We pointed out that this is a generic problem for string theory, and this is true. I mean, it's still, even though at that time our argument was very roughly to say all the fields they coupled with gravitational strength and they have to get a massive supersymmetry breaking, so the only scale they can be is probably the gravitino mass, that is 1 TeV, and then they can cause a problem because they can either overclose the universe or decay so late that they ruin photosynthesis. And in our case, we have the 3 types of fields, and the problem is different for them. The U and S fields are usually trapped in the minima, so they are not that problematic for this. The heavy moduli, they are heavy, much heavier than so in that sense you would say they are safe. But usually if the field is heavy, because the bound from the cosmological model probably is something for 10 TeV. If it is heavier than 10 TeV, you're more safe. But if it is much heavier than that, like 500 TeV, it can decay into gravitinos, and then it can overproduce gravitinos, so that's a problem. However, in our case, we can compute the decay rate to gravitinos, and it's very much suppressed, so there's no problem. This is probably problem for this. The only interesting or problematic case is this large volume modulus, the light one, which has a mass of 1 MeV and couples gravitationally. So that is subject to this cosmological model problem. Yes, that's what I gave the picture first. Yeah. They couple to the standard model, they decay into photons.
What happens during inflation? Can I imagine a huge amp like jump which would displace me in a completely different vacuum?
It could be, you know. I'm studying things after inflation. So inflation I don't touch now. I just see what happens on these particles after that.
MEV speed of matter.
Sorry?
Is that decay today?
The MEV guy, yes.
10 to the 27.
10 to the 25 seconds, so I like that. So I guess it's just better. Yes. So for this cosmological model, I have to confess that after 13 years I didn't think about it. And just recently, coming back to this question, we discovered this paper of Light and Stewart. It was my ignorance, I'm sure many of you know it. There is something called thermal inflation that I found very compelling to solve this cosmological model problem. And they have the idea is to have a potential, the standard potential with a thermal component. For a field, the important thing is that the field has a vector much bigger than its mass. And actually, these people consider that the mass of 1 TeV and the vector of 10 to 11 GeV. So it was 10 years before ours, which is very clear.
But you don't know how the thermal field will be established.
Exactly. You have to see. You have to look for a field that has the proper things of thermal equilibrium. We can do. There are examples actually. I have candidates, but actually, Gia, if he is around, he told me he actually has a model with brane inflation presented to it. It's called thermal brane inflation presented to it. A few years ago. And the nice thing about this is that you have the number of e-folds is the log of the ratio of the two scales, and if this scale is much bigger than that, you get something of order of 10 e-folds, and that's enough to dilute these fields and solve the problem without causing any changes in the original inflation at the higher energy. So this I think is very interesting, and I think it's worth exploring more because, as I said, the cosmological model problem is something generic. It's not only in non-other models, but essentially any other simplification we don't have to face this problem. Okay, so how much do I have? 10 minutes? 7. So, so then imagine that this problem has been solved, the topological model problem for this field. So can this field have any implications at low energies? So you can test it. First of all, because the decays to gamma, you have to see how there's a lot of information about this diffuse gamma ray background. So we compare here the field we say is a 41 MeV, so it can be 0.7 MeV, it can be 2 MeV or so. So we compare the production of gamma gammas for different masses of the corresponding field, and this is the bound given by the Comte about the background gamma ray. So that puts some constraint on well, it works better for a lighter high, but it puts constraint on the number density, on the contribution of high to the energy density of the universe, and in this form. So that's a constraint that we have from the background. But the interesting possibility is the possibility of this 1 MeV or for the 1 MeV models to be the source of this 511 kV line that have been observed for about 30 years or so, and more recently by this SPI integral, SPI in this integral satellite. They have this very clean 511 kV line, and it's coming mostly from the bulge of the center of the galaxy, and there is not a good explanation for the origin of this line. And one possibility is to have dark matter decaying or annihilating produces that, and people have proposed those scenarios in the past. And in our case, it so happens that we have a field that has precisely the right properties, because the mass is exactly in the right ballpark, which is the order of 1 MeV, so it can decay to plus and minus, and this 511 kV gammas come from the annihilation after the E plus, the positrons going through matter, then at some point they slow down and they annihilate and produce the right 511 kV line. And so we not only have a particle of the right scale. I have to emphasize that this scale it came out when we imposed to get a TeV scale to solve the hierarchy problem at low energies. This is something that we couldn't play with. It has to be this mass. But most importantly, also the coupling. A particle like this would couple naturally to electrons and positrons, but also to photons. So if you couple to photons, you will more naturally will decay directly to photons rather than the E plus minus, because this one has to come from the E plus minus analysis. However, as I showed you in the previous transparency, the coupling to gamma gamma is suppressed. The branching ratio is 0.9 for the decay into E plus and minus compared to gamma gamma. So that means that it is dominant, the decay of 2 E plus and minus, and so this particle has the right mass and the right couplings to give you the 511 kV. And furthermore, well, I have we computed the couplings here. As I said, this is the ratio of the branching ratio of both. This is the branching ratio, the national branching ratio, but this is the real power of the line, because for E plus and minus, you get the positronic state, it goes into 3 gamma 75% and 2 gamma 25%. And so you have to reduce only the 2 gammas are the ones that give you the signal. And from that, we can see that the intensity, doing our calculations roughly, essentially we get a further 8 times 10 to the minus 5 photons per centimeter per second. Whereas the integral bound on an observation of the direct line, that means of the particle producing a monochromatic line studied onto direct decay, is 5 times 10 to the minus 5. So they are in the same ballpark. So in principle, you say, well, if you take the numbers exactly, you have this model, this particular stream model 11169 is true lab, although you cannot take 0 to this factor of 1 or 2. And so, and furthermore, we know that the numbers have to be of this order, but not that big, or not that different from this, so that we can convert that into a prediction, actually, because that means that if this is the explanation of the 511 kV, then we have to see the in the near future, this other decay, the direct decay in the monochromatic line of this particle directly into photons, because that we are close to the limit.
Are these particles cold enough?
Yes, because yes, there's a bound that they have to be more than 3 MeV or so, and that is well, these particles are more or less that it's more of that. Okay, so let me just conclude. So yesterday we heard a lot of talks about saying that we are living in exciting times for cosmology. I want to say also we are also living in exciting times for extreme phenomenology. And the reason is because of the progress that has been made in the last few years about model stabilization. The problem that we were always facing for 20 years or so, and I think now it's real progress, and we have to show what kind of implications, different implications this can give us, both for LHC canon physics and for cosmology. So as I told you, the soft terms were time calculable, and then you can get a very rich phenomenology that you can contrast with LHC. Complete ways that we can differentiate our models with the standard M-Sugra models by constructing the mass of the particle and so on. There's a very distinctive model like cosmology, as I told you. Even though the moduli are generic, it was always assumed that they would essentially take the mass of the orbital gravitational mass and they couple to gravitational strength. But once you do the complete models, you can see the physics is completely different. They couple in completely different ways, and the masses can be as large as 100 TeV and as small as 1 MeV. So the physics is very interesting. Well, I mentioned that we have complete models of inflation, even though we have this open question. And then this model-independent light models corresponding to the large volume can have can be a possible explanation for the 511 kV. I have to say that I think it's the first time you have a complete candidate with the right properties. Because people have proposed something like a random candidate that could do the job without having a well-motivated candidate, but this one comes all the way from Smith. And the nice thing that it has a prediction that, first of all, that the monochromatic lines should be seen. If this is the explanation for the 511, then the other monochromatic lines should be seen relatively soon. And there are other questions. One of them I have to insist is this fight between some things prefer the string scale to be m-God, and other things prefer the string scale to be 10 to the 11 GeV. And so we have to find a way to either to have something that either combines both possibilities or gets the inflation at this scale, or just try to get phenomenology from this, even though there requires some affinity. I have to insist, I didn't say it explicitly, but we could also try to make connection with the talk of Cliff Borges this morning, because the scale, the string scale at 10 to 11 GeV was to get the soft terms. Well, but you can also get 1 TeV as a string scale, and then put the standard model on anti-brane, which is the very supersymmetry. That would be something close to what we have been talking today. So in general, there are many things to be done, and I think this is an interesting area. So thank you for your attention.
Fernando.
Yes?
I've got just one worry. Since your moduli is a volume model and it couples to everything, couples to, in a way, it also, it's there, also governs my, say, SU3 coupling, all sorts of coupling. Since it is so light, I can imagine that during inflation, it could be driven very far away from its minimum. So, for instance, I can completely change my SU3 coupling, I can completely change my SU2 coupling. It's not a quantum just thing which you can hide in threshold corrections and so on and so forth. So, say for instance, one example I can find in your case would be that I do not know whether the spell-around transition may take place at as high as 10 GeV or as low as 10 2 GeV. So I can really completely match.
I think it's well, this is an interesting question, something to investigate. But let me remind you, we don't have the standard model on the large cycle, which is what the volume is. We have the standard model on the small cycle. So the couplings of these fields to anything in the standard model is very weak. So that's the thing. So it's always separated by 1 over m Planck times the log of m Planck. Because even further separated than m Planck. It's very big. But still, I think it's worth exploring the earlier universe cosmology.
Coming from the Taylor potential and
yes.
a little bit lost, then it will be e to the power 5, so something like exponential.
Yes, but the field in the Taylor potential constantly log. So when you have e to the k, You have negative powers of the volume.
Okay.
So you have, and the negative powers of the volume give you how much suppresses with respect to the time. And so that's how we get it.
Anyway, it's something that you have to check perhaps.
I think yes, to get a full basic cosmology, I think you have to see a universe. I'm worried now about this.
I mean, it's not because of the standard moduli problem, it is slightly beyond that actually. Because the standard moduli problem is the particle production at late time. But
yes, it's something. That's a good point. Yes, I didn't explicitly say it, but there are several ways of predicting. Either putting that in brain as KPLT did. You have also with Renata and Steve putting adding deep terms. Actually, for this deep terms part, we wrote a recent paper in January because there is this issue that people say that, which I think is an interesting comment, that you say you want to have you have fewer terms than the deep terms are also zero. And so it's hard to use to victim. In our case, it works perfectly well because the F terms are non-zero. The ADS is already non-zero. So the D terms are non-zero. So it works fine. So yes, so it is ball dependent. If you can see how it works, how these D terms are generated, and then depending on the model, you have where the D terms are put. If it is wrapped in the large cycles or small cycles, you get different things. In some cases you get lifting, in some cases you don't get lifting. But at least you don't ruin the large, the fact that you get the large volume. And of course there are other proposals, but we can probably try and say something.
Who wants to say something now?
Okay,
I
good.
have a question. Can you explain again precise assumptions under which you think you get fiber blind masses?
Yes, is that yes. We had the Keller model are the ones who break percentage. Where the complex structure model are the ones that give you the Yukawa. The Yukawa couplings are the ones that depend on the complex structure model. They don't depend on the Keller model. And those are the ones that give you the non-universality, because that's the thing that gives you flavor in the rotation.
Well, but I mean, you have computer dimensions like scalar potential correction to actually build soft masses, right?
I think, well, universality we have is approximate. I said approximate because it is to leading order. Of course, we have to see in the next order we have how badly it's broken. Then I think it's broken. It's broken by an expansion of one of the small module, small cycle, and so you have to see if that approximation is good enough to give you something. Yes, and yes. There is another issue that we are also addressing in the recent paper is that to be more realistic, to actually think about the standard model, we know that the models that we construct on these 7 brains on 4 cycles, they come out like equivalent of the second brain. There will be brains with magnetic fluxes, and then the magnetic fluxes can induce some dependence on the complement. The complements may depend on the magnetic fluxes. So we are in this, well, actually the joke on this right now that one argument is that usually in the brain of angles, each generation comes with the same angle. So that angle is also universal. But so at the moment it's only the words, subject to manipulation.
Well, let's thank Mr. Bailey.